In all likeliness, you've heard Hammond organ before. It's one of the most popular instruments in contemporary music, up there with the likes of the guitar, the piano, the drums and things like that. Unfortunately, its sheer size and bulkiness make it an extremely impractical instrument, so there's a very high demand for a convincing sounding synthesised organ. The aim of this project was to create such a synthesised organ, and so today I'm going to be discussing with you some of the basics of how I implemented this. Now, the characteristic sound of the Hammond organ comes in fact from its accompanying Leslie speaker. The Leslie consists of two speakers, one for high pitched notes, one for low pitched notes, rotating in a circle inside of a big wooden cabinet. This rotation has two effects on the sound. Firstly, since the direction of travel is constantly changing, there's going to be a time varying Doppler effect, shifting the perceived pitch of the sound in much the same way as for a police siren. Secondly, since sound travelling along longer paths is going to sound quieter than sound travelling along shorter paths, and since the path length from the speaker to the ear is going to be constantly changing, there's also going to be a volume modulation as well. Now, these modulations of volume and pitch are the two most important effects that we need to consider if we're going to be creating a Leslie synthesizer. Armed with this knowledge, it's not too difficult to construct a mathematical model of a Leslie speaker. Instead of working with the quantities of pitch and volume, we need to instead work with the much more physically relevant quantities of frequency and amplitude. Once the equations for the frequency and amplitude modulations have been obtained, we can draw plots of how they vary in time. The frequency modulation looks like this, and the amplitude modulation looks like this. Now, as you can see, they have very similar shapes. However, if you look at them in a little bit more detail, you can see that they're not exactly the same. One of the main differences between them is that there is a 90-degree phase difference. This basically means that a peak on the frequency modulation plot will occur a quarter of a cycle before a peak on the amplitude modulation plot. This is actually quite easy to understand when we think about it carefully. The peak on the amplitude modulation plot occurs when the speaker is at its shortest path length from the ear. This happens when the speaker is at the front of its circle of rotation. For the amplitude modulation, however, the peak occurs when the Doppler shift is greatest. Now, this happens to be when the speaker is at the side of its circle of rotation. So you can see a quarter of the circle between these 2 points. Looking at the equations for the frequency and amplitude modulations in a little bit of detail, you can see that they're highly dependent on the relative positions of the speaker and the listener. So the sound that is going to be heard is very dependent on where you are sitting to hear it. In order to incorporate this three-dimensionality into our equations, we need to turn to something called binaural theory. Binaural theory says that the way we determine where a sound is coming from is by subconsciously comparing the differences between the sound arriving at each ear. So, for example, if I heard a sound louder in my left ear than my right, it must be coming from somewhere over to my left. Now, our brain is very good at using even barely perceptible differences in the sound to determine exactly where the sound is coming from. But the main two differences are the time difference between the sound arriving at the two ears and the volume difference. Using just these two effects, it's quite possible to get a general feel of where the sound is meant to be coming from. So, putting this all together, we can construct a mathematical model of the Leslie speaker in such a way that we can get some sense of where the speaker is meant to be. Once this has been done, we can put this into a synthesizer program using a language called Csound. Now, the structure of Csound itself means that some approximations and simplifications have to be made to the model, which ultimately result in a less realistic sounding synthesizer. However, all the main features of the instrument are there, as any good synthesizer should have. So, here is the synthesizer.